All right. Well, good morning, everyone. Today is our second day of the advanced concepts in designing and retrofitting energy efficient data centers today.
Right. Thank you, Andrea. So at the end of last class, we continued to about 12:30. We left off right before starting to discuss liquid cooled servers and their associated design requirements. In that last 30 minutes of the class where we ran over the scheduled period, we talked a bit about the central plant types that we typically use for serving a distributed air side cooling equipment, things like IRCs and active and passive rear doors, as well as other systems and data centers. You'll obviously have access to those slides, but if there are any specific questions related to those slides, feel free to put them in the chat. I mean, ultimately, we probably have more content than we can cover in 6 hours, so just consider that it's okay if you missed it. What we're sharing now doesn't necessarily require that you have attended those last 30 minutes of the class, so don't worry about that. We also saw that I think there was maybe one question that popped in right at the end of the last class before we signed off. That we weren't able to read. It literally came in as we were closing the meeting. So if that attendee is here today, feel free to repost that question in the chat and either Jeff or I will answer it. All right. So we're going to spend probably the first, 30 minutes, an hour here talking a bit about liquid cooled servers, since this is something that's become very prevalent in the industry just within the past 3 or 4 years. And we'll start by just giving a high level overview of what it is we're talking about. What is the distinction between a liquid cooler and an air cooled server? And it really comes down to what heat transfer medium is interfacing directly with the IT gear that's generating the loads. And so with an air cooled system, you essentially have air that's blowing over finned heat exchangers that's picking up heat off those CPUs and GPUs and other components. In a liquid cooled system, you have some process fluid. It could be propylene glycol. We'll get into that in a little bit. It could be deionized water. It could be a refrigerant that is flowing over those devices, those GPUs and CPUs, and picking up heat via something called a cold plate. And so the heat transfer is directly from the CPU or GPU to the process, a liquid fluid. So this is a example conceptual layout of how that works. And so what we're seeing here is that we have some cold plate, which is essentially a very, very, very tiny pipe or set of pipes through which fluid is passing through. And there's a bunch of heat transfer surface in those cold plates to allow as much interface between the CPUs and GPUs and the cold plates as possible. And so we're talking about systems that have micro channels that are on the order of 50 to maybe 100, 200 microns in width. And so obviously that has additional impacts on how the distribution system works, because we have to be filtering down to a very fine level, which we'll talk about a little bit later. So essentially we're sending the fluid through these cold plates. Those cold plates are interfacing with the CPUs and GPUs. There's often a thermal paste that's between the cold plates and the compute device. This diagram here shows that we have some sort of isolation between what we'll call the FWS, or the facility water system. That's the term that's sort of been adopted by ASHRAE for the cooling loop that's at the facility level that is not interfacing directly with the servers. And then the TCS, or the technology cooling system, which is on the other side of a heat exchanger and is sending a process fluid to interface with the CPUs and GPUs. And so we'll talk a little bit more about that in just a moment. So here's just kind of a more exploded view of what's happening at the chip level between an air-cooled versus liquid-cooled server. In this case, we're actually seeing some fairly high temperatures. We're saying up to, say, 130 degree Fahrenheit water is being distributed to these devices within the server, and then it's leaving at 140. Now, that's theoretically possible. I can tell you, however, that most of the owners that we've been working with on these systems are not running them anywhere near that warm. A lot of times we'll be operating in a band that's more like 90 degree Fahrenheit supply to the servers and 110 degree return or thereabouts. And on the bottom, we just have an illustration of how the heat transfer systems differ between an air-cooled and a liquid-cooled server. On the left, you can see that in this older chip, we have a lot of air-cooled fins, right? We're trying to increase the amount of surface area as much as possible to allow heat transfer off of those chips and to the air. So we have these large stacks of fin devices we're pulling air through. On the right, we have an example of a liquid cooled server where we have those cold plates that are stacking directly on the CPUs or GPUs in this case, I believe, and supply and return off a little header within the rack itself, going to each of those individually. Okay, so another piece of terminology that's, I think, come out of ASHRAE originally. It could be wrong on that, but it's at least what ASHRAE has adopted. And what you'll find in the industry is this term of a coolant distribution unit, or CDU. And it's effectively the device that is isolating your facility water system, the FWS, from your technology cooling system, the TCS. And the reason we're doing that is largely because the fluid cleanliness requirements differ significantly between what you might have going to, say, a typical cooling coil and an air handler versus what the fluid requirements for what you're sending to again, that cold plate with those really tiny micro channels. And we'll talk about fluids in a little bit, but essentially there are two levels of CDUs to think about. One is a multi-rack CDU where you have this essentially a heat exchanger, a set of pumps, and a control valve and some other sensors in a box that isolate the FWS from the TCS and then distribute fluid out to multiple server racks. And we could have one CDU, for instance, serving maybe 5, 10, 15, 20 liquid cooled server racks. The other option that's very common is an in-rack CDU, where you have the facility water supply going independently to each rack, and then a smaller localized TCS loop that's serving just that rack. So this is often located at the bottom of the rack. You'll have something that takes on the order of 4 rack units of height. And so it'll slot into the rack. And within that, you'll have just a smaller version of a set of pumps, a heat exchanger, control valve, and some controls to make the whole thing work. We'll talk about the distinctions and the control strategies between these two different types of CDUs in a little bit. So here's an example blow up of a CDU schematic for a multi-rack CDU from one of the major vendors in the industry. And so the industry has sort of coalesced around the idea that CDUs are a commodity that is produced by vendors and then sold to contractors and installed in the field. It's a little bit odd, and we'll talk about the fact that it doesn't need to necessarily be that way. Really, what we're dealing with here, again, is a couple plate and frame heat exchangers, control valves, and pumps. And those are things that an engineer can certainly specify and have this system be what we'll call stick built in the field, meaning that we're independently selecting all of those devices for the application requirements and then having the contractor assemble them in the field, as opposed to buying this system in a box. And there are certainly benefits of doing that way, which I'll talk to on the next slide. But starting here with an example from a manufacturer, what do we have? So on the left side of this diagram, we have what again, we're calling the facility water system. And on the right side, we have the technology cooling system, TCS, that's serving multiple racks. And so the way that a multi-rack CDU is controlled, there are really two critical components. One is the supply temperature control for the TCS within the CDU. Let me pull up a pointer here. So in this case, what we see is there are 3 supply temperature sensors integral to the CDU. And there are 3 of them because these are typically employed in data center mission critical applications. And therefore there's a requirement that there be redundancy such that if any one of these fail, that we have backups. And a lot of times for critical sensors, you'll see 3 instead of 2, because with 3, you can isolate where you have a problematic sensor. With only 2, you just know that the sensors are different. You don't necessarily know which one is out of calibration. In any case, we have supply temperature sensors, and those are essentially our control point. And what we're doing is we're modulating these valves on the facility water side of things in order to maintain some target supply temperature going out to the liquid cooled racks. And then the other thing we need to be concerned about with this system is making sure we're providing sufficient flow to those racks. And that's handled via differential pressure control. So in this particular CDU, we don't actually have a single device differential, a DPT, a differential pressure transducer across the supply and return. What they instead do is have two gauge pressure sensors. There's one on the supply, and then they have redundant gauge pressure sensors on the return. And they use that to calculate differential pressure. And we're maintaining some differential pressure set point across the CDU to ensure that as valves open and close, the pumps speed up and slow down to maintain that DP so that all the racks get their required flow. And all the other appurtenances that are required for this system are included in the box. Things like expansion tanks, air vents, filtration, all of that is included integral to the CDU, which minimizes the amount of scope outside of that the contractor is responsible for. That said, again, it's not critical that that CDU be something that you buy out of the box. You can design your own CDU, and this is something we've done for customers. I guess the question is, why would you want to do that if they're manufactured products? Well, surprisingly, perhaps one of the things that we found is that it can actually be more cost effective to do it this way. Those CDUs are shockingly expensive for what they are. Again, we're just talking about plate and frame heat exchangers, a couple pumps, control valves, and some sensors. And we've found that where we've done these on a custom or stick-built basis, it's often less expensive for the job. The other benefit we get from doing it this way is that we're able to independently spec all the critical components for the application-specific requirements. So one thing you'll find with those example CDUs I was showing on the previous slide, they're basically a fixed set of SKUs that the vendors offer. So you can't have mix and match different options for control valves and pumps and heat exchangers. You're basically getting the same set of devices, irrespective of what your design conditions are outside of that box. It's certainly nice to be able to select those things independently based on the application requirements. One example might be that we've run into is that a lot of times we may have a very high design load off that CDU, but we also need to be able to control stably when we're only operating at 5 or 10% of the design load. And one of the problems that we've seen with off-the-shelf CDUs is that the control valve is well suited for a design condition or port load, maybe 20, 30%, but it tends to hunt and it's not tuned well for a low load condition. And so with a custom CDU, we've actually done something that's not shown here, but we'll have, let's say, a set of parallel control valves, something like a 1/3 and 2/3 valve, so we can get better control both at high load and low part load conditions. We can also specify pumps that have lower or higher pressure capabilities based on what we know about the cold plates in the servers that we are ultimately serving. So it just gives you a bit more flexibility and something you might want to consider in your designs if the owner is amenable to it. A lot of times what you'll find is owners have standards and they've standardized around a known product because they're comfortable with it. And so you just have to spec that even if you don't think it's necessarily the best thing for the job. Okay, stepping back a little bit, ASHRAE has defined these temperature guidelines or temperature classes, whatever you want to call them, for liquid cooling. And as I showed in an earlier slide, a lot of liquid cooled servers theoretically could allow up to 130 degrees Fahrenheit supply and over 140 degree return. However, that's not how many are operating in practice. And what you'll find is a lot of owners tend to be more conservative and actually ask for lower supply temperatures. And the lower the supply temperature, the more mechanically intensive or cooling intensive the process becomes, right? If I'm trying to generate 17 degrees Celsius or 63 degree Fahrenheit supply water, well, in the vast majority, pretty much any climate, that's going to require that we have some form of compressorized cooling for at least some hours of the year. So we might end up with a system that uses air water cooled chillers in combination with a waterside economizer or dry coolers as an economizing means when ambient conditions allow. However, the warmer we make or allow the temperatures to be, the less energy intensive and simpler our mechanical system can be. So as an example, if, for instance, the owner allows us to send 90 degree Fahrenheit water in the facility water loop to serve those CDUs? Well, in a lot of climates, that means we can use a system that doesn't have any chillers. It just has cooling towers. We very frequently do this in the Bay Area, for instance. And then the further you push this up, so say it's 104 degrees Fahrenheit, well, that would, in many climates, or at least in cooler northern climates, potentially allow you to eliminate the cooling tower altogether and move to a system that just uses dry coolers. So now you've eliminated the water use associated with this process as well. And then the warmer you make the temperature, you also increase the opportunities for direct heat recovery. Obviously, if we have a chiller system, we can use the heat we're pulling off those chips and then rejecting via the condenser water loop, perhaps with the heat recovery chiller to serve some process load. But if the temperature coming off the chips is already in excess of, say, 110 degrees Fahrenheit, there's a good chance that we can use that heat directly for heat recovery, going to either some process, or perhaps we're cooling the admin side of a data center, or heating the admin side of a data center building using something like reheat coils or a dual fan, dual duct, hot deck air handler. It just allows us to do the warmer we can get the water to return off those chips, the more efficient we can operate our heat recovery systems, and the more efficient, frankly, we can operate our cooling system. So this diagram is a bit obfuscated. So I actually took some real world data to make this, but because those data are under NDA, I couldn't show you what the exact points were on this curve, but this is more or less exactly the supply temperature versus flow relationship for a real world liquid cooled server product. And what's interesting is that for whatever reason, the industry has coalesced around this idea of representing delta T's instead of just talking about the delta T as it varies for a given supply temperature to the servers in terms of liters per minute of flow per kW of IT load. And frankly, it means the exact same thing. For a given process fluid, if you know what the LPM per kW value is, that translates directly to a delta T. And the higher the LPM, so the amount of flow per minute in liters per minute through the server for a given amount of load on the server in kW, the higher that value is, that means the lower your delta T is. Obviously, a lower delta T, that's not a good thing because it means that you are generally going to need more fluid, a higher flow rate in order to accomplish a given amount of cooling. And so what you see for this example product, or I've fuzzied the numbers up a little bit here, is that as the supply temperature increases from about 25 degrees Celsius up to 45 degrees Celsius, we see that there's more than a doubling in the flow required to accomplish the same amount of cooling. So there is a little bit of a trade-off there. The higher the supply water temperature you design for, the less mechanical energy you're ultimately going to need to accomplish the cooling, but you are going to be doing it at a higher flow rate, and your pipes sizes are obviously going to increase as well accordingly. So what is the process fluid that we're using for liquid cooling? I guess most people, if they didn't know anything, they would guess, well, we probably just use water. And water can be used, but in most cases, water isn't just water. If you are seeing they're being used directly, it's most frequently deionized water to eliminate the impurities associated with the regular water, right? Because regular water just coming out of your tap has a higher mineral content, which contributes more to scaling, which is less than ideal when you're dealing with a system that's, again, very narrow process channels going through those cold plates. However, the industry has not really coalesced around DI water because DI water has its own challenges related to corrosivity. When deionized water comes in contact with air, which there will invariably be some of in any process circuit, even if you have air separators, the pH of the water decreases and it becomes more acidic, which can speed up the rate of corrosion in the loops. So what we see on the vast majority of our jobs is the use of some sort of inhibited glycol mixture, the most common one being something like PG25, which means 25% propylene glycol. You could also use ethylene glycol, but it seems like the industry has picked propylene glycol because it's non-toxic, whereas ethylene glycol is toxic. You can purchase PG25 as a pre-mixed mixture, meaning it comes in these drums that are already 75% water by volume and 25% propylene glycol. Or you can get PG25 directly as a 100% concentrate and then mix that with deionized water to create your process fluid. In the applications that I've been involved with, it's always been pre-mixed. I think because the owners, they'll specify a certain process fluid. So in our specs, we'll list 2 or 3 options that have been pre-approved by the owner, because if they know that that those process fluids are going to work for their servers in conjunction with the wetted materials list that they provided us, that tells us, hey, here are the list of materials that are accepted for our liquid cooling loop. It's important to account for the fluid properties of your process fluid, particularly if they're glycol in design, because they do differ significantly from those of water. The higher your glycol content, the lower the specific heat capacity of the process fluid and the lower the conductivity as well. What does that mean? Well, it means that for a given amount of heat transfer, your flow rate is going to be higher than it would be for water. And it also means that for a heat exchanger, because the conductivity is worse, that heat exchanger is going to be bigger if all the other variables are held constant. Another consideration with glycol is that it has higher viscosity than water. That means that for a given flow rate, the friction loss in your piping network is going to be higher. So it impacts the way you design your piping as well as your pump selections. So again, it's absolutely critical that you account for glycol in any heat exchanger selections and your hydronic circuit design. The process fluid also impacts what the acceptable wetted materials are for the system. So these things go hand in hand. Usually if you're working with an owner, you'll first identify what the process fluid is that they want for the systems. Again, a lot of times it is PG25. And then based on that, they may provide you, if they have a materials expert on hand, with an acceptable wetted materials list, or you can refer to ASHRAE TC9.9 Guidelines, where they're also publishing acceptable wetted materials lists for different materials, or excuse me, for different process fluids. Here's some language that I pulled from a manufacturer about why they prefer PG25. And they say it provides good wetted material corrosion performance per ASTM D1385 and D8040. Those are 2 test standards. I'd be lying if I said I knew much about them, but that's their justification for liking at PG25. They also note that it is biostatic at 25% volumetric concentration, which means that in addition to being corrosion resistant, it has a tendency not to develop or have bacterial growth within the loop that can also lead to fouling and other problems. So this was the question that I had early on when we were proposing what we'll call custom CDUs to owners, is why do we even need CDUs to begin with if we can have a loop that is clean and perhaps isolated from, say, something like a cooling tower system, where you obviously have exposure to all sorts of impurities? It really comes down to a few different things. One, it is just that water quality isolation. So we need to make sure that the loop that's getting sent to those the liquid cooled server cold plates is appropriately filtered. So if we have cold plates that we know are 50 microns, well, we're probably going to be filtering down to at least 25 microns, perhaps lower. Generally, as a rule of thumb, you want to filter to at least 1/2 the width of your cold plate size. So in this example, again, we know our cold plates are 50, so we're filtering down to 25. And then it provides for that biological growth and corrosion control. Another benefit of using CDUs is that it allows you to chunk the system within a data hall. So instead of, say, using a system where we can do fluid quality control at a global level using just one heat exchanger that isolates the full data hall from, say, a cooling tower system, the challenge there is, well, what if you have a problem with the loop at the rack level or along one header. Well, when that happens, you potentially need to shut down the entire system in order to address this. With CDUs, you're more or less chunking the data center into smaller groups. So if you have a problem with, say, biological growth, or you have a leak at one rack or on one header, you can isolate that system and take it out of service without potentially taking your entire data center out of service, needing to drain down the loop to deal with some microbiological issue and then bring it back online. So there's a clear benefit there from uptime when you're just trying to minimize the impact of local issues. And in colo facilities, providing CDUs or CDUs provide a nice point of demarcation for the responsibility of the colo provider, which is generally just providing the facility water to the CDU, and what is maintained and oversaw by the owner of the racks within the facility. And so that'll be the clear demarcation point. The facility is responsible for the FWS, and the server owner who's leasing the space is responsible for the TCS. Some of the cons associated with this paradigm are higher first costs. The more CDUs you have, the more costly the system. The more you can group the systems under a single distribution loop, the less costly, generally speaking. You're buying more devices, so there's more complexity. There's potentially more maintenance. Reliability, I think that you could argue both ways. Energy efficiency. So this comes back to the idea of a custom versus a stick-built CDU. A stick-built versus off-the-shelf CDU. A lot of the off-the-shelf CDUs have heat exchangers with fairly poor approaches. If I'm specifying a heat exchanger for this application, I would generally be looking at a 2 to 3 degree Fahrenheit approach. A lot of the CDUs that we are working with manufacturers on have approaches that are more like 6, 7, 8 degrees Fahrenheit at similar design conditions, which has a downstream impact on how we design our facility water system. If, for instance, we know what the owner wants going out to the servers, but we know that there's going to be an 8-degree approach across the heat exchanger instead of a 3-degree approach, that might impact whether we can do the load entirely via cooling towers or dry coolers, or we need to introduce mechanical cooling in the form of chillers, as an example. So this one, I think, Jeff, do you want to speak to? I think I can just scroll through these for you.
Yeah, sure. Okay, so this is a liquid cooling data center that we worked on a couple of years ago, and Brandon talked about pros and cons of CDUs, and this data center went without CDUs. And so basically what they have is cooling towers only, going through heat exchangers, and then basically one TCS loop, if you will, or one process fluid loop serving all of the racks. And to get around some of the issues that Brandon talked about with impurities and filtration, they went with things like stainless steel piping, which is going to have less risk of both corrosion and impurities, high filtration, high levels of filtration using cartridge filters, which surprisingly had pretty low pressure drop when you put them in parallel and use enough of them. It was designed for a certain pressure drop across the racks. One of the main drivers for this was to try to get rid of chillers, and the CDUs might have been what would have pushed them over the edge to have to run chillers to design with chillers. And so that's why they went in this direction. They end up being able to meet all the loads at a 73-degree design ambient, 83 coming off the towers. So just one example where you don't have to go down the route that most folks are going with the CDUs.
Yeah, I mean, conceptually, you could view this thing as one giant CDU, right?
Yeah, right. You could think of it that way. But the alternative would have been to have downstream CDUs, right? They've got a set of heat exchangers to separate the condenser water from the process, but you could also put individual CDUs at each branch or even at each rack.
Right. And had the condenser water going into the white space to serve those CDUs.
So all the liquid cooling we've been talking about so far is using basically cold plates. There's another technology out there. We don't personally have much experience with it, but I understand it's gaining traction. And that is, rather than having these plates with very small channels attached to each CPU and GPU, why not just dunk the whole dang server in a big tub? And that's basically what this technology is. It's called immersion cooling. And of course, that tub of fluid has to be non-conductive, so it can't cause electrical issues with the gear. But there are fluids like mineral oil that have good heat transfer properties and are non-conductive. And potentially this has potential to be quite efficient and even maybe even lower cost, because you're getting rid of all kinds of tubing and cold plates. Obviously there's other challenges in terms of how to organize and arrange your servers. They have to basically be in these sort of horizontal server racks rather than a vertical rack. And I don't know a whole lot about how the cabling and so forth works. So again, I don't have much experience. Maybe others on the call can share some of theirs, but I think we're going to be seeing more of this in the future.
Okay. I guess actually we're calling this slide liquid cooling summary, but it might be useful to step back because we didn't at the beginning of this, or I didn't address the kind of the why behind liquid cooling. Why are we seeing this evolution relative to what the air cooling that we've been doing now for 30, 40 plus years? The real driver here is density. As loads per square foot of server are increasing, it's becoming increasingly difficult to handle those loads with air-cooled systems. And liquid cooling affords a means of handling these higher densities. We're regularly seeing now in our jobs racks that are 80 or more kW of cooling. And on some of our test lab jobs, we're actually being asked to design for the potential of up to 300 or 400 kW per rack as an upper end of things. And even perhaps larger cluster systems that are multi-rack slots, but are more than that as well. So the densities are really increasing markedly. But again, we shared some of the typical temperatures or the temperature classifications that ASHRAE has published. In practice, what we're seeing is more like a range of 78 to 90 degrees Fahrenheit going out to the servers in the TCS loop. That may be subject to change with time, and I would certainly like to see these numbers creep up because it increases the flexibility with which we can serve these loads. As Jeff just provided in his previous example, we were able to handle the loads with just cooling towers in the Bay Area because of these process temperatures. But perhaps if they'd pushed it something like, I don't know, 110, maybe 120 degrees Fahrenheit, it would have been possible to eliminate the cooling towers and just do it with dry coolers. Right? Another thing to consider is the delta P across the cold plates. And so cold plates, in contrast to a general, say like a chilled water coil, where you might expect a pressure drop on the order of 5 to 10 PSI, tend to have much higher pressure drops. And that's because, again, they have these really, really tiny microchannels. So the amount of surface area relative to the cross-sectional area is high, and therefore there's higher losses through those cold plates. And so we can see anywhere from 15 on kind of the lower end design up to 40 PSI of pressure drop through cold plates. A lot of the projects that I've been working on recently, they've asked us to design around 30 PSI of drop through the cold plates to give them flexibility for different products as they evolve. And then one really key consideration is that most liquid cooled servers are not 100% liquid cooled. These things range across a wide spectrum. So you might have cases where a liquid cooled server is 70% liquid cooled and 30% air cooled, or it could be on the other extreme, 95% liquid cooled and 5% air cooled. And this is just because there are certain components within the server where they don't have cold plates. And so those are still potentially generating heat that needs to be picked up by an airside system. So these data centers become increasingly complex because you not only have the liquid cooling system, you also perhaps have you do have another system that's handling the air cooled loads, whether those are IRCs or rear doors or flooded aisle air handlers. You generally have a hybrid scheme that has both liquid and air cooling. So some of the advantages of liquid cooling relative to air cooling, one is efficiency. You're dealing with fewer fans, right? So you're blowing around a lot less air. You are perhaps pumping more process fluid, but on balance, there is a net decrease in energy use associated with distribution. You're also reducing, integral to the servers themselves, the number of server fans, right? So in a 100% air-cooled server, whatever the facility is moving in airflow, that's also what the servers are moving in airflow generally. Well, if we're going from something that's 100% air-cooled to something that's 20% air-cooled, in theory, we're reducing the airflow in the data center by 80%, and we're also reducing the airflow in the servers by 80%. So we have a lot less of those server fans. These data centers also tend to be much quieter. I don't know if you've been around some of the GPU systems that are high density air-cooled racks. They are incredibly loud. And in general, air-cooled data centers, the higher the density, the louder they'll tend to be. It's nice from an operator perspective to be working in and around quieter equipment. Some of the disadvantages, where owners are requiring that you design around low supply temperatures to the TCS because perhaps they're conservative, or maybe they are, just using a single existing chilled water distribution loop to serve both airside equipment and liquid cooled loads. Well, when you do that, it actually becomes less efficient because you're eliminating the potential for airside economizing. This next one I'll just defer to. This is a concept of power bursting that we're seeing in AI data centers, and Jeff will speak to this on the next slide. And another disadvantage is degrading delta T, and I'll talk about that more in the context of how the controls work for liquid cooled racks on a later slide. But suffice it to say that in general, we're seeing in low and lightly loaded liquid cooled conditions that these systems have low delta T's, which means we're using more pumping energy and perhaps leaving some economizing on the table that we could be otherwise capturing, or we have historically captured with air-cooled systems. There's often a cost hit because we're sending processed liquid to every rack. We're seeing the dollars per square foot in liquid cooled data centers on the mechanical side be very high. Yeah, so those are just some of the major ones. I'll keep moving here in the interest of time. Jeff, how about you speak to this since you've seen this recently?
Yeah, sure. So just to follow up on some of the comments you just made about efficiency, I mean, in my experience, liquid cooling is a newer field or newer developed compared to air cooling. And right now, I would say liquid cooling is really considerably less efficient because people are being more conservative, maybe in terms of those water temperatures. Like Brandon was saying, you could specify W45, but really we're seeing like W27 and even lower. And what we're also seeing is that it's very common to serve both of your liquid cooling and your air cooling with the same water, right? The same chill water that's going around your facility. It can be pretty expensive to have separate piping, separate systems at different temperatures. And so the air side is sort of dictating the total water temperature. And so even if your racks can operate at a higher liquid cooling temperature, the air side, rear doors and crays and so forth, need the lower temperature for their requirements. And now I would say liquid cooling is basically a step backwards in terms of data center efficiency. And our challenge as an industry is to try to move it forward, look at ways to separate air from liquid cooling with different water temperatures, ways to push up the temperatures. And one of the challenges we're seeing, I wouldn't necessarily liquid cooling, but with AI, which is where the boom is right now in data centers, is AI behaves very differently than other types of data centers that I've been involved in. Almost all the data centers I've worked on have had very stable IT loads, right? The IT load literally grows over months and years as the data center gets built out. AI and the nature of learning modules is a very variable load. And as you can see on this slide, there's this new phenomena called power bursting, where you can have the IT load can double in seconds, literally. And this is new ground for us, right? It's a big challenge because we have things like sequences that we've been using for many years to stage chillers on and off. And they usually have things like, well, wait till the current stage of chillers is run for 20 minutes and make sure, and then check to see if you're starting to run out of load, and then slowly bring on the next chiller to avoid disruptions. You'll be dead in the water with an AI system if you use the old sequences. And we're for us at least breaking new ground with things like jump staging chillers. We might change it, go from running a plant that has 10 chillers. We might go from running 2 chillers to running 8 or 10 chillers in seconds, because the load has literally gone up 50 or even higher. And I've seen this happen. We're doing some work on an AI data center, and the load will jump 80 to 100 megawatts in seconds and then drop back down. And so we need much more rapidly responding staging and sequences. Another thing that we feel is probably going to be required to keep the load satisfied and to avoid and to keep the plant with any chance of operating efficiently is thermal storage. And so we're designing primary, secondary chill water systems with a thermal storage tank in the decoupler, so that a sudden increase in secondary loop flow rate, the tank can sort of act as a flywheel, if you will, and pick up the load change while the primary tries to catch up and bring more chillers online. Interesting times that we're going through and challenges that we're coming across with the new AI boom. Brandon?
Yeah. So thanks, Jeff. We'll spend a couple slides here talking about a little bit more about TCS control strategies. And I have a bunch of words on this slide, but I'm going to skip over them and use the schematics in the next slide to talk through this, or to walk through this. But I just want to include this here for you guys' reference. So we'll talk about the way that this is done for in-rack CDUs and what some of the better options are that we see for in-rack CDUs. And we'll then do the same for multi-rack CDUs. So from left to right is what we kind of see is the evolution of in-rack CDU control. The first one on the left here, number 1, is an example of what you can buy right now on the market. And the way this is generally controlled is that within the CDU for the TCS loop, you have a set of constant speed pumps that are distributing flow out to multiple servers within the rack. And so that means that irrespective of what the rack load is, this flow rate is constant. And on the facility water side, what we're doing is controlling a valve to maintain a constant supply temperature going out to these loads. So in this example case, the supply temperature going out to the loads is 35 degrees Celsius. And stepping back for a second, in this example, for all the numbers you're seeing on the screen, we're working with a load condition. We're estimating here of 50% of design load on the rack. So at design conditions, what we'd have instead of a delta T at the rack of, a temperature differential between 35 and 45.8 degrees C, at design, this would be on the order of 56 or 57 degrees C, right? And so the way this system is working is as the rack loads increase, the supply temperature is staying fixed and the return temperature is floating up. Now, the most obvious flaw with this common design is that on the facility water side, they're using a three-way valve instead of a two-way valve. So what does that mean? Well, we have some water or some process fluid, whatever. We get a marker out here. So we have our facility water. Some of it's going through this heat exchanger and the rest of it is getting bypassed through this bypass leg of the three-way valve and blending back. So in this example scenario, our delta T on the facility water side is less than the delta T on the liquid cooling side because of this bypass leg. So where we might have a 10, 11 degree delta T, I guess, again, we're talking in terms of Celsius. At the liquid cooled rack, we're only getting a 5.4 degree delta T on the facility water side. And why does that matter? Well, it matters because what I want to do is maximize the return water temperature that's going back to my plant, because that allows me to, if I have a plant that's doing any form of economizing, increase the amount of load that I'm being served with, that's being served with the economizer. And then looking beyond that to being able to directly serve loads with this temperature, say in this water in a heat recovery application. Well, we want it to be as warm as it possibly can be for use in that application. Well, what is the next evolution beyond that? Well, this one's pretty straightforward. And again, this is something you can buy in the market now, which is in-rack CDUs that eliminate the bypass leg. So they have a two-way valve instead of a three-way valve. So there's no reason you should be doing this first option. We still see many owners doing it, unfortunately, where they're buying these things preemptively. So it's owner-provided, contractor installed equipment. Try to stop this whenever you can, because there's a major benefit in at least going to option two. And so from a controls perspective, this isn't all that different, right? We're still constant flow through the racks, and our valve is still on the facility water side. It's still controlling to maintain a target supply water temperature on the TCS side. The difference here, though, is because we no longer have this bypass leg, our delta T on the facility water side has increased markedly. So here we're now getting basically double the delta T on the order of 11 degrees Celsius, which is about the same as the delta T that's on the TCS side. So this is great from an economizing and heat recovery perspective. But it's still not the best we can do. Now we're kind of in options 3A and 4A. We're getting into kind of future where we'd like to see the market going. Really, what you're trying to control at the rack level is temperatures at the chips, right? I don't really care whether 35 degree Celsius water is going to the chips. What I care about is making sure that those chips don't exceed whatever their target operating temperature is. And so one way you could potentially look at this is instead monitoring the return temperature coming off the rack. And as long as that return temperature is within acceptable range, you know that the chip temperatures potentially are within acceptable range. So you could, in theory, control your facility water valve to maintain a return temperature and set up a supply temperature. That approach, however, isn't foolproof if the loads within your rack, within the trays in the rack vary. So if I have this guy operating at 100% load, but the rest of these guys at 0% load, well, this could be problematic because I'm sending fairly warm water to it, and it may be that the return temperature off this individual rack is too high, but the rest of them are in an acceptable range, which in turn causes the overall return to be acceptable, and we potentially cause a problem. So a scheme that's relying on return temperature alone could pose issues in systems where servers within a given rack do not tend to vary up and down in unison. And so That's something that you would need to work with an owner to understand. There is, however, some potential to still use this sort of scheme if you're also introducing power monitoring at the rack levels. If, excuse me, let me step back. If you were introducing individual temperature monitoring at the server level, so going over to 4A here, what we're showing is that perhaps over some sort of network connection, we are monitoring the chip level temperatures. If I know what the temperature is of each chip, then I can use a worst case chip temperature to in turn control my facility water valve. And so that would sort of be the panacea here. We have not yet seen an owner be willing to provide those data from their servers to inform the control of the TCS of the facility water valve. And I don't know if we ever will. But another option that we're looking at and considering is perhaps monitoring individual rack powers or monitoring individual server powers or monitoring rack level power, because this kind of gets back to what Jeff was talking about on the previous slide about power bursting. If we know that the load is potentially step changing between 20% of design up to 80% of design in a matter of seconds, well, if our valve is waiting to see a change in temperature, that might be too late. So we could potentially leverage power data to inform what we're doing with our valve and specify a quick acting valve so that we can do this almost instantaneously. And this valve would want to be a pressure independent control valve, meaning that a given position for a mechanical pick fee correlates to a given flow. So we could essentially, based on a step change in power, use that to immediately drive our valve to a target position before we ever even actually see a change in the chip or return water temperature. And so essentially what we're trying to do with these newer options on the right, 3A and 4A, is come up with a scheme that allows us to increase the delta T on the facility water side to the extent that's possible in order to increase the efficiency of the mechanical cooling systems and drive heat recovery. So we can potentially do that same thing that we were illustrating for in-rack CDUs, for multi-rack CDUs as well, just in a different way. So this evolution, again, progresses left to right. The first example here is what we'll call standard practice. And this is more or less what we've been asked to do by an owner that I've been working with now for many years. Their preference is to maintain a fixed delta P across the rack header, because this allows them to, as they're adding or removing racks, ensure that adding or removing servers within a rack, that each of those servers is maintaining design flow. And they do this with something called an energy valve. And an energy valve is more or less just a fancy pressure independent control valve that, instead of using mechanical regulator, uses the flow meter to introduce pressure independence. I won't get into the nuances there, but I will suffice it to say that an energy valve is generally more expensive. And because it has a flow meter, they'll add in these temperature sensors, which allow it to be the energy valve, because it can now monitor flow and temperatures and therefore monitor the heat transfer across the rack. Even though this energy valve could be controlled to a flow or something else, what they're doing is they're using it typically as a standard valve and controlling a DP. And then you also see here that we have two shutoff valves at the rack level, and these are automated valves, and they'll typically be fast acting valves that are controlled by the building automation system to close if there is a leak detected either underneath the rack or along these drops, such that the leak is isolated to just the rack. And so what are some potential means of improving this? Well, in our mind, the first option would be eliminating the energy valve and just using a standard mechanical pick fee. You're getting equivalent performance from this system, and you're reducing cost. You don't really need to have an energy meter at the rack level. Most racks are typically going to have power monitoring at the rack level already via an in-rack PDU, perhaps via a bus plug. Those are very common things that you'll see in a data center. So you don't really need the power monitoring, and eliminating the energy valve reduces your costs significantly. Another potential clever solution, one that we didn't come up with, but we've seen recently, is for the shutoff valves, replacing one of those shutoff valves with a check valve, right? Because if there's a leak here and we close this guy, well, then the leak is going to obviously drain down the pressure in this local circuit. And because the rest of the loop is pressurized, that check valve will be maintained shut by the rest of the system. So you could potentially reduce some costs this way. Not any different really from what we shared on the previous slide. Because we're maintaining a DP across these racks, and unless you're adding or removing servers, the racks are more or less just fixed orifices. What you'll find in practice is that these valves are essentially controlling to a fixed position. And the valves are therefore more or less acting as balancing devices. So if the load on the rack is low, then the DT in the rack is low. If the load on the rack is high, then the DT will tend to increase. But that again leads to this problem where we have degrading DT at the facility water level. And because we have degrading delta T, we're potentially doing less economizing and we are limiting our heat recovery potential. So how do we resolve that? Well, we use similar strategies to what we proposed on the previous slide. We could, instead of controlling to DT, monitor the return water temperature coming off the rack. This scheme would work well if we knew that the rack loads didn't power burst, and we knew that the individual server loads within the rack were varying in unit rack. And so we could use power data to preemptively open this PIC-V to where it needs to be to serve the load, in addition to leveraging the temperature data as a failsafe.
And now would be a good time to take our first 5-minute break. So
okay, this next section, we're going to kind of go through a hodgepodge of HVAC design considerations. And because we have a lot of content to cover today, both in this section and others, I'm going to move through it fairly quickly since we spent a bunch of time on liquid cool. So the first thing we'll touch on is redundancy, which invariably comes up in data center design. Some of the lingo that you'll run into was developed by a group called the Uptime Institute. They provide certifications for data centers as well as practitioners, and they've come up with a 4-tier model. The higher the number, the more fault tolerant the facility. A tier 4 facility is quote unquote fault tolerant. It has 2 end systems, which means everything is fully redundant, both on the mechanical and electrical side. So if you need 5 chillers, you have 10 chillers. And those systems are compartmentalized in the sense that you basically have 2 separate plants. So if there were some huge issue where you had to fully shut down the room with the first system, you could cut over to the second system. We don't see these all that frequently. More common option that many owners go with is a tier 3 or concurrently maintainable data center. These have at least N+1 systems where any component can be taken offline for planned service. And they tend to have 2 or more electrical and mechanical distribution paths. So since I'm speaking to mechanical engineers here, this might be 2 chilled water supply distribution mains and return mains entering and leaving the plant room, as an example. Tier 2 is a step down. They're still N+1 systems, but they do not have fully redundant electrical and mechanical distribution paths. And then tier 1 would be basic site infrastructure with no redundancy. And systems don't necessarily slot into any one of these. Owners make decisions based on their individual risk tolerance. So you often see systems that blur the line between a tier 2 and a tier 3 facility. So I haven't updated this recently, but as of 2019, there were only 380 Uptime Institute certified facilities. You don't have to have Uptime Institute certification to be a true data center. Many others will claim tier equivalency the same way many owner operators will claim lead equivalency instead of going through the full lead process. So the tiers should really be used as a guideline during design, not necessarily hard and fast rules. So where is redundancy valuable? Well, perhaps most obviously for any components that are most likely to fail. And next, the second category would be any components that may need maintenance. So an example would be a chiller. A chiller is going to need quarterly maintenance. So it would make sense in a data center context, even if you were willing to roll the dice with the redundancy to only provide in chillers, because you know you're going to have to take something offline for maintenance. Distribution paths that may fail or require maintenance. So again, this might be, if you're fairly conservative, having a second distribution path to all of your loads or mains out of the plant room. So any chilled water leak allows you to isolate a section of pipe instead of taking the whole system offline. So some examples for where redundancy might be implemented would be chillers, pumps, cooling towers, air handlers, and probably most importantly in my mind, controls. And we'll talk about controls in more detail later in the class. So here's a simple example just showing redundant piping. So in this case, the plant room is up here. This is where all the chillers live. And we have two sets of supply and return mains that are leaving the plant room. And then we have ring distribution at the roof serving the air handlers so that any one section of pipe can be taken offline with continued service to everything. So how much redundancy is warranted? Again, this is often a client-driven consideration. So early in the design process, when you're establishing a basis of design, this is something you need to work through with your owner. For most enterprise facilities, N+1 redundancy makes sense for mechanical components that aren't in service continuously. So an example would be chillers in a plant with an airside economizer, because we know that if we have an airside economizer, there are going to be a lot of hours when not all the chillers will be online and we have an opportunity for maintenance because ambient conditions, the weather will allow it. For systems that need to be in continuous operation, N+2 is a logical target, because if something needs to be in continuous operation, but it requires maintenance, that means there will be times where you have to take at least one device offline. And if you have one device offline, you still want to have some level of redundancy should some sort of fault occur. So N+2 provides you with that level of backup. And then N+1 will often make sense for systems with internally modular components. So if we're thinking about something like an air handler, it might have multiple supply fans. It might have multiple of those supply fans split up across multiple VFDs. So if there's a VFD failure, it doesn't take that entire air handler offline. It only takes part of it offline. And when you have internally modular components, it's important that you don't layer redundancy on top of redundancy, because doing so adds cost. As an example, let's say we have two air handlers that are N+2. If you have N+2 air handlers, then you have both concurrent maintainability, meaning something can be taken offline, and a fault can occur while you're doing that maintenance work. So it wouldn't necessarily make a whole lot of sense for that system to have internally modular components, because you're layering additional redundancy on top of the system that probably isn't warranted. If, on the other hand, your air handlers were only N+1, then adding internal modularity would provide an additional level of safety to protect against any fault during a maintenance event. So I'm guessing this isn't going to work, so I'm just going to speak through this. And we're short on time here. Which option would you choose for a data center that requires 1,000 tons of chilled water capacity and an owner that desires N+1 redundancy? Well, there are a few different ways you could skin that cat. You could provide two 1,000-ton chillers. You could provide three 500-ton chillers, or you could do four 333-ton chillers. So let me take you through how I think through this. I probably wouldn't go with the first option, because it is likely going to perhaps cost the most, because you're buying the most total tonnage, but also because it's likely going to have operational problems under low load conditions, because our turn down might be only to 100 tons. So when this data center is first starting up, it could be that we have the chiller cycling itself to death. Options 2 and 3 are a little bit, the decision is a little bit tougher. It again is true that if you go all the way to option 3, you're buying less chiller capacity, but you're also buying more pipe. You have more pipe laterals to each chiller. You have more controls. So in this case, I would actually bet that options 2 and 3 of those two, option 3 is going to be the one that costs more. You're getting the same level of redundancy. And in terms of low load turn down, these likely aren't going to be all that different. So my intuition, short of getting actual chiller selections, would be something like option 2 would be the best for this example case. Okay. The next thing I want to touch on is how to properly select an air distribution scheme for air-cooled servers. And earlier in the class, we went over, and particularly on Monday, we went over a number of distribution schemes. We talked about underfloor systems, overhead systems, close coupled systems, flooded aisle systems, and all of them have their place, and their choice is a function of load density. So how many watts per square foot we're dealing with, what sort of spatial constraints you're working with, the use case, whether it's a rack lab or a bench lab or a full-on enterprise data center, and what your budget is. So underfloor systems, starting with them, tend to be optimal for colocation facilities because they accommodate changing areas of peak loads easily. And what do I mean by that? Well, the way you shift capacity around an underfloor data center is to move floor tiles that have perforation. So it could be the case that you have a new colo customer who needs a high amount of airflow. Well, you just allocate them more underfloor tiles to give them that capacity. If you didn't have an underfloor system and you suddenly decided you wanted to put a bunch more load on a single cold aisle in a flooded aisle data center, well, that might be problematic if that aisle is already maxed out. You don't have the flexibility to easily add or remove load. Underfloor systems tend to pair well with either ground-mounted air handlers or overhead air handlers that are ducted to the underfloor. So there's some flexibility there, and they can be a viable option as a result for multi-level facilities. So another option would be overhead distribution. We find this to be particularly useful in retrofit contexts with limited floor space and a good amount of overhead space. One of the major constraints with overhead is that we are now fully ducting systems, and that can be some pretty gigantic ductwork when you're getting up into reasonable levels of density. It doesn't necessarily make sense for greenfield facilities or high density facilities, but in retrofit context, it can make sense where you're, say, adding a small rack lab in an existing building. We find that it couples well with service from house systems because most house systems are going to be overhead. Think about a typical VAV reheat system. So you could potentially have a 100 kilowatt data center that you're serving off of an existing office air handler that has an airside economizer. So you're getting the benefit of economization to that data center. Flooded aisle designs, we find these are optimal for single level greenfield data centers where we can have grade mounted air handlers because we can plop the air handlers immediately adjacent to the side of the building and blow air directly down the cold aisles. They don't tend to be as flexible as underfloor systems because, again, we can't easily reallocate capacity based on where we find increasing or decreasing loads. So they're not as good for multi-tenant facilities, but they are good for enterprise facilities that are owned by your Apples and your Googles and your Microsofts of the world. Close coupled systems. So these would be in-row coolers, rear doors. They tend to be good selections for space-constrained data centers with no access to outside air. The typical use case might be a building where we have a data center that's buried on the first floor in the middle of the building because we have all the occupants on the perimeter because occupants want natural light and servers don't necessarily care. But when you do that, it makes it very difficult to leverage airside economizing. So you need to employ different strategies like waterside economizing for those close coupled loads. They also tend to be a good choice for multi-level data centers because it becomes, the more levels you have in a data center, the more difficult it becomes to distribute large volumes of air to multiple floors. Okay, changing gears again to talk a little bit about another design consideration, which is things to consider for chilled water plant design. The first would be, what's your distribution scheme? The two main options that we see in data centers are either variable primary or primary secondary. I think if we were teaching this class 2 years ago and we didn't have this burst loading issue and the need for consideration of thermal storage, variable primary was the way we went on most data centers because it was first cost effective, and at least relative to constant primary variable secondary, the pumping energy use was lower as well. Now with data centers that have IT loads and burst loading, we tend to find that a primary secondary system works well because you can put the thermal storage in the decoupler and use that as a means of load smoothing to, as Jeff was describing, allow your chilled water plant to catch up to those sudden changes in load that are being addressed by that TES that's in the common lake. Another distribution consideration is redundancy of piping and whether you want to implement ringed distribution. So this is largely an owner-driven decision. At this point, I've seen a couple leaks in my career. I have not seen enough to say that redundant or ringed piping is the right solution for all owners. Where you do have a risk-averse owner, one benefit perhaps of ringed piping is that if they're willing to do this, you don't have to have fully redundantly sized mains going both directions. You could say size each of the mains for 50% of the flow, such that if there's a failure, yes, you might have to take something offline and data center load might have to decrease some, but you still retain some level of redundancy under pipe failure scenario without having to take the full facility offline. For a lot of rack lab use cases, that's been a solution we've gone with. On the pumping side of things, we see a lot of engineers liking to specify what we'll call a lineup where you have a chilled water pump and a condenser water pump dedicated to a chiller. We personally aren't big fans of that approach because it means that when a pump goes offline, you're losing your chiller as well. So our preferred scheme is to use a set of headered chilled water pumps and a set of headered condenser water pumps. That way, if you lose a pump, you're just losing a pump. You aren't also losing a chiller when a device goes offline. Delta T. So we've talked a lot about the importance of high return temperatures. And high return temperatures, again, are important because they allow us to increase the degree to which we can economize. So on the water side, it's important that we select our coils for high delta T. And how do we select coils for high delta T? Well, we use deeper coils with more rows. We make sure we have at least 10 fins per inch, so fairly high fin density. And we also work with coil vendors to properly circuit coils to get that high delta T. Personally, I'm okay with waterside pressure drops on the order of 20 to 25 feet through a chilled water coil if it allows me to get a 20 plus degree delta T across the coil. That's more important from an overall efficiency perspective than keeping the pressure drop through the coil low. Battery rooms. So the purpose of battery rooms in the context of data centers is to provide energy storage for ride-through UPS systems. And so this means that if there's a power outage, that UPS will kick in and use those batteries to provide continued service to the data center for a minute or two or longer, until the generator systems can get online. There are some unique considerations that have to be accounted for battery systems. And those include thermal control and life safety control. And so historically, the most common form of batteries in battery rooms were valve regulated lead acid batteries. And these batteries off gas a small amount of hydrogen. And if the hydrogen in a room gets to a certain level, that poses an explosion risk. And so these rooms require one of two strategies. One is to just have a fan in the room that's always running and sized at 1 CFM per square foot. The other is to use hydrogen monitoring in the room and have an engineered system where you size the fan per the load, what you expect the hydrogen load to be under a worst case scenario, and turn that fan on and off based on monitored hydrogen concentration. This particular consideration is changing as the market moves a bit away from VRLA batteries toward lithium ion batteries, because lithium ion batteries do not have that same hydrogen off gassing constraint. So you don't necessarily have to provide the same exhaust systems for those batteries. Regardless of the battery type, it's important that you work with the electrical engineer to get submittal data so that you understand what the operational constraints of the batteries are, because what you'll often find is that thermally speaking, they require a lot cooler temperatures than a lot of the other electrical or IT gear. So in this example submittal, we see that this manufacturer is saying that they want the batteries to stay under 77 degrees Fahrenheit for the majority of their service life and to never exceed an operational temperature of 122 degrees. The second is generally easy to achieve. The first, 77 degrees, it's easy to achieve, but you need to be cognizant of what that means to the rest of your systems. You wouldn't, for instance, want to specify your entire data center or your entire electrical rooms even to operate at 77 degrees when the rest of the gear can operate perfectly fine at over 90 degrees. So what we'll often do is make sure that these batteries are isolated in their own room that's separate from the rest of the electrical gear and control that room to a cooler temperature and use perhaps a different system. So we're not allowing the tail to wag the dog. Maybe we have a small DX system that's doing the cooling for this room so that we can serve the rest of the space at the rest of the electrical rooms at 90 degrees using 65 or 70 degree chilled water. All right. So I covered most of this. Chilled water storage. What are the whys behind introducing chilled water storage? One is it mitigates risk from chiller failures because it gives you something to ride through should a chiller unexpectedly trip offline. Gives the operators an opportunity to get that chiller back online. It also gives chillers an opportunity to restart after power failure. So perhaps instead of providing UPS backup to your chillers, you're okay with allowing the chillers to go offline when utility outage occurs and wait the 2 to 3 minutes it takes for the generators to turn on and those chillers to boot back up. Well, you can use the storage as a means of riding through that outage. And then another benefit is a means of mitigating AI power bursting, as Jeff described in detail earlier.
So thermal storage, as Brandon said, has a few valuable features, particularly now with the issue of AI power bursting. We're finding it to be a pretty critical component of the system. We've seen some fairly complicated thermal storage designs, including charging modes and discharging modes and lots of valving to do that. And here's our preferred scheme for thermal storage. So this is a plant we're working on that has primary, secondary. Here's the secondary pump. And so the secondary leak goes like this, if you will, in a circle. And then here's the primary loop with our primary pumps, waterside economizer heat exchanger, our chillers. And so the primary loop goes clockwise, if you will, as opposed to the secondary, which goes counterclockwise, which makes this piece of pipe here, the decoupler, flow can go either direction, depending on whether primary or secondary is higher flow. And then we put the thermal storage in that loop. And so this valve here would be shut pretty much all of the time. These valves would be open all of the time. And in normal operation, you want your primary to always exceed your secondary. So this flow rate would be going higher than this flow rate. So the flow in the decoupler would be going in this direction. And so we'd be putting cold chill water supply into the bottom of the tank, and the tank would be nice and charged, and we'd be taking some water out of it at the top. Not a lot of flow would be in here. You generally want these flow rates to be similar. And so mostly we'd be taking hot secondary return, blending it with a little bit of cold primary return, sending it to our heat exchanger and our chillers. But if we had a power burst scenario, these pumps would have to respond very quickly. They would speed up. And now the secondary flow would exceed the primary, and we would now be going this direction, sending hot water from the secondary return into the top of the tank, pulling cold water out of the bottom of the tank and sending it back to the loads. And so we'd still meet the load, and this tank would basically start to discharge, if you will. Like there would be hot water sort of moving its way down towards the bottom of the tank. But in the time that as that's moving down, that gives us the opportunity to crank up our chillers, crank up our primary pumps, and basically start pushing backwards, right? Pushing the cold water back in to the point where we're then pushing more water into the bottom, right? That this primary exceeds the secondary, and we'd be recharging the tank. So that's our sort of simple thermal storage scheme. So another consideration with chill water plants is makeup water, particularly for water cooled chillers, right? If you've got cooling towers, you have the risk of losing water. And what do you do to maintain your makeup water reliability? One option is to start with multiple city water feeds. So we worked on large plants where they've got water connections to the municipal system from multiple locations, such that if one city water feed goes down, you might still be able to get water from the other one. Reclaimed water. A lot of jurisdictions like Santa Clara, for example, have a separate reclaimed or recycled water system, purple pipe, they call it. And you can have both potable water and reclaimed water feeding your makeup water. One, because the reclaimed water is cheaper and it's using recycled water, but two, because it gives you more reliability. We worked on a number of systems that have well water, either as the primary or the backup source, right? And so now you'll have potable water and well water as your two water sources. Rainwater and stormwater. This isn't 100% available, depends on how much rain you get, but in wetter climates, this can provide a significant amount of backup reliability. And of course, it's a green feature to be able to capture the rainwater off the roof or the stormwater off the site and use that for makeup water. Storage tanks, just like that thermal storage tank for chilled water, you can have a similar tank for condenser water. You can also use the same tank for both. But in an emergency, that chill water thermal energy storage tank could be isolated from the chill water system and used to feed into the cooling towers. Taps for tanker trucks. If nothing else, it's very cheap and easy to put in some connections so that if water needs to be brought in by truck, you'll have a way to get it in your system. And KISS, keep it simple, stupid, is our motto for all kinds of design issues. But again, with makeup water, we've seen some very complicated schemes, and I'll show you what we've used on a lot of our projects. Okay, so here's our simple scheme for makeup water storage. And this was actually a scheme we used not on a condenser water system, but actually on an evap cooling. We'd use this on both direct evap cooling and indirect evap cooling. But the same concept applies basically to any system using evaporation, cooling towers, or direct or indirect. And we happen to have, in this case, 3 city water feeds that we fed into a very large distribution ring that ran around the perimeter of a very large data center. And so we had all of the city water feeds configured with a pressure reducing valve to maintain a certain pressure set point, right? And they were holding a certain pressure in this ring. And then we also had this storage tank over here, which was fed by a control valve that was maintaining a water level in this tank. And then a pump that pulled out of that tank and fed into the same ring. And this pump was holding pressure in the ring that was higher than the set point on these PRV valves. And so in normal operation, you generally want to flow through your storage tank because you don't want it to sit stagnant for long periods of time, waiting for the city water to fail, which it probably will never fail. So you need to constantly sort of refresh your tank. And the best way to do that is to just use that as your primary source. And so primary is to maintain the flow level in the tank and to use this pump to hold this pressure at a higher level that basically shuts the check valves from these these other city sources and makes this the primary. And then if this pump ever fails, this pressure drop will go down as the loads pull off of the ring. And these check valves will naturally open up by themselves and feed the loop. And so it's sort of a fairly foolproof kind of scheme. We've seen schemes where you have control valves from the direct feeds that then have to open up when the system detects certain conditions. And this is basically all automatic for the most part. So that's our scheme. Okay, so we've talked about lots of different design options for both air and liquid cooling. How do you come up with the best option for your data center? Well, generally what ideally you'll want to do is a life cycle cost analysis or a TCO, total cost of ownership analysis. And of course, a big part of that kind of analysis is energy. And there are lots of package simulation products like Energy Plus and IES and eQuest out there. We actually have done most of our recent analysis simply using spreadsheets. The envelope load is trivial and kind of where these types of modeling software would be needed. But since we don't need to model the envelope load, we basically just take the weather file and we bin the data in terms of dry bulb and wet bulb bins. And so we might have 200 bins instead of 8760 hours. And then for each of those bins, we'll model different loads. Title 24 and ASHRAE 90.1 say when you're doing data center modeling to model a load profile that just looks like this, quarter of the time at each of these IT loads. And we're then able to do very sophisticated custom sequences, things like a dew point economizer lockout, custom component curves for IDEC. We showed some of those curves already, I believe. Yeah. So anyway, that's what we use. Other folks, feel free to share what you found works well for you. Okay. Here's a sample lifecycle cost or TCO analysis for one of the clients that we've worked with. And there's a lot going on here. This is annual energy in PUE units, right? Power usage effectiveness. And this happens to be in North Carolina, and it shows data for a whole range of systems. To me, one of the striking things about this slide is that direct evap cooling. So this is North Carolina direct evap cooling. And then I don't remember what this set point is, but this was using the 85-degree supplier set point. The gray is electrical and miscellaneous. So that's constant among all the options. But in terms of the mechanical system options, direct evap cooling is by far the most energy efficient. These ones down here all had air side economizers, either using DX or chilled water. I would say those are all in second place. So if you're doing direct only or air economizing, that's the most efficient scheme. We looked at a couple other so here's these two here are IDEC, necessarily particularly efficient, certainly not compared to direct. SciCool is a product from Nortec, and they're very tight with their proprietary nature. So it's kind of hard to understand exactly what it is. SciCool, we talked about Monday. That's Munter's. Sorry, I got that wrong. SciCool is Munter's refrigerant economizer. Here's the Nortec system. And then down here, these last four are variations on air-cooled chillers. And so air-cooled chillers, let's just compare these air-cooled chillers over here to these direct evap cooling, probably 5, maybe even 10 times as much annual energy use. So a significant difference in efficiency. Here's the same cooling options compared on their peak power. So one of the really important factors is how much electrical infrastructure and generator capacity is going to be needed to serve the mechanical system. And again, direct evap cooling, by far the winner. Those airside economizer options, which were second place for energy efficiency, are probably in last place for peak power. So you're paying a lot for air-cooled condensing on your mechanical cooling system in terms of the switchgear and the generator sizing at your site. I'm going to skip this slide in the interest of time. This is the same system is sort of summarized on their power and water across the climates we looked at. And you want to feed, of course, your life cycle electricity and life cycle cost of water into your total TCO analysis, which is going to include things like your equipment cost. This was a comparison of different IDEC options that we did several years ago now, but you're going to obviously want to include the full life cycle cost. So maintenance, general contractor impacts, electrical service impacts, facility architectural impacts, structural impacts, et cetera, et cetera. One other thing that, I said about simulation is that it helps you include the cost of the water and the water consumption. An interesting feature about direct evap cooling is that the amount of water is highly dependent on what supplier temperature you're using. So this happens to be data for Albuquerque at two different airside delta T's and at the air handling level. And obviously the higher the delta T, the lower the water use because the air comes back, you're using less air. And then if you raise your supplier temperature from say 68, which, is not that uncommon in data centers, to say 80 degrees, you can get about a 75% reduction in the amount of water you use. Another strategy owners try to use often is increasing the cycles of concentration to try to reduce water use. It's much less effective or has much less of an impact on the supplier temperature. So here's at different supplier temperatures, you can see relatively small changes based on the cycles. Obviously 100 cycles is not possible. That's just sort of showing the theoretical best possible scenario. And my sort of takeaway from this is that it doesn't really make a whole lot of sense to spend a lot of money and complexity, things like water softening systems, to try to increase from 3 to 5 cycles, even up to 10. It's a fairly minor improvement in water use. And this is one of my favorite slides because it shows water use of a direct evap system compared to a cooling tower system, right? If you're using just chilled water for all of your cooling, a direct evap system uses a tiny fraction of what a cooling tower would use. This is in gallons per megawatt IT load on an annual basis. And we already talked about how you can drop your water use by raising your supplier temperature. And some sort of fun facts: a typical fast food restaurant uses 20 times as much water as a megawatt of direct evap cooling. Even a typical car wash, even the average US household is using a lot more water than you would be using. Of course, that's per megawatt. So if you had a 20 megawatt data center, you'd have to multiply these by 20. But the point is, direct evap cooling sometimes has this impression of using a lot of water. It actually is very, very little water compared to like water cooled chillers. We have worked with clients who have things like a water cooled chill water plant serving all the load, who are interested in reducing their water use. And I'll just say up front that water is still relatively inexpensive, and trying to reduce water use isn't a life cycle cost effective strategy when you compare it to the cost of the equipment and the extra energy to to reduce your water use. But there are certainly options. There are things like a hybrid cooling tower. So this cooling tower can evaporate water when it's hot out, but when it's cool out, it basically can serve as a dry cooler, or as a dry cooler. And this is more of a dedicated dry cooler that has the ability to evaporate water under the worst case conditions. And we looked at schemes where we've even retrofitted dry coolers in series with the existing cooling towers, right? So this was, don't change out the towers, just add some more dry coolers purely as a water saving feature. Again, increases energy use and cost, but we're working with owners who are 100% renewable. Some of them are even looking at nuclear power for their data centers. And so water is increasingly on. I'm going to skip this slide in the interest of time. Brandon, I think you were going to.
Yeah, I think
Right.
this was this spot, Jeff, because you have the other slides hidden.
Okay.
I'll take it over and talk about commissioning here. So we're going to spend the next little bit here talking about controls design and commissioning. We'll get started and then we'll take a break at 11 for 5 minutes. I personally think controls are incredibly important in any context, but particularly in data centers, because our combined experience is that the vast majority of faults, just as a guess, probably 90% of faults that we've seen in data centers are the result of controls issues more so than mechanical issues where just adding redundancy would have solved the problem. So within a data center context, there are really two options that owners have when selecting the type of controls to install. Those would be a DDC system. And so by DDC, we're thinking about your ALCs, your Allerton, your Johnson controls, your Delta, those sort of systems. And then the other option would be PLC controls, something like Allen Bradley, Rockwell automation PLCs that you would then layer on top a SCADA system like Ignition or Allen Bradley. And so those are, or Wonderware. So those are the two main options that owners have, and there are certainly pros and cons to each that we'll touch on. And there, regardless of whether you're looking at DDC or PLC, there are two real main viable means of achieving fault tolerance from a controls perspective. One is what we'll call redundant central control, and then the other is distributed fail-safe control. And these don't have to be employed exclusively. They're often used in concert in a data center context. So by redundant central control, what we mean is that there are two controllers or processors that are available to run a given system in the event that one were to fail and go offline. By distributed fail-safe control, what we mean is that we may not necessarily have two redundant controllers for a given application, but we have isolated the amount of things that are being controlled by any one controller, such that if one controller goes offline, we're only losing a small amount of overall automation. So you could, for instance, consider a case where we have 6 air handlers serving a data hall. Each of them has its own controller. If one goes down, we likely have fail-safe responses for that air handler, but we have automation retained for the remaining 5 air handlers because they each have their own controllers. So speaking a little bit to DDC versus PLC controls, what are some of the pros and cons? Well, for DDC controls or commercial controls, we typically find that the first cost is going to be significantly lower, both in terms of the cost of the equipment but also in terms of the cost of the installation. Sometimes it can be a third or half as much as you would pay for an equivalent PLC system. We found that these DDC controls can be successfully employed on data center projects. And in some cases, we find that they're easier to use and maintain because it's kind of like you can think of it as the difference between an Apple system, perhaps, and a Linux system, right? The Linux system might give you a lot more flexibility, but it has to be set up right from day one. And the people who are setting it up and the operators need to be able to handle that complexity appropriately. DDC systems tend to be more of a limited sandbox to play in and give you less flexibility as a result, but they're often easier to work with. That said, we're finding that DDC controls are becoming increasingly flexible and fault tolerant and are now starting to support some of the functionality that was once strictly the domain of PLCs. As an example, DDC controllers now in many cases support ring network topology. And by that, we mean a system whereby you have two communication paths to a network device, such as if one of those communication paths were to fail, there's still another means of getting the data to that device along the network. And DDC controllers are also starting to support the concept of what we call synchronized redundant manager controllers. So historically, it was strictly PLCs that could have two managers functioning and fully synchronized, such that if one were to fail, the control loops on the other would pick up right where the former lead controller was operating. Now, a lot of that functionality can be accomplished with DDC controllers as well, though that functionality varies from one DDC vendor to the next. Industrial controls also have their own benefits. One, in some cases, is a lot of times a kind of a higher grade implementation team, meaning both the install team and the programmers. They might come from just the mission critical space and therefore be dedicated to this realm. Whereas on the DDC side, you might have a programmer who was 2 weeks prior working on the controls for an office building, and now he's being asked to do the programming for a mission critical data center. And probably the most compelling argument for industrial controls that we've found is that it's easier to find global support for a single platform. So a lot of our enterprise customers, they prefer PLC controls, not necessarily for any hardware reason, but rather because they know they can get support for their controllers in a rack lab in Santa Clara, as well as in a production facility in Taiwan and a data center in Utah. You can get support for some of the bigger PLC players globally, whereas that may not be true of some of the DDC vendors who have approved contractors in certain areas of the country or other countries worldwide. There are still areas on the automation side where industrial controls are ahead. They have things like self-tuning algorithms. There are cases where they have more processing power available in controllers. So you can use redundant central controllers that are chock full of programs instead of distributing those programs down to lower level controllers. They tend to be more robust devices. On the flip side, they can be harder to program, and they generally do require some form of third-party SCADA interface. Again, I mentioned Ignition as an example earlier, as well as something like Wonderware. They can support some more flexible redundancy schemes. One piece of terminology you'll hear in the context of PLCs that's a bit foreign to DDC is this RIO, or remote I/O panel, where you can have a couple redundant central controllers that are communicating over a very fast network to these I/O panels that don't have a whole lot of brains, but just have the inputs and outputs going to the controlled devices. All right. And so here's an example.
It's 11 o'clock. Should we take a break?
Oh, thanks, Jeff. Yeah, we can stop here and come back in 5. So what's on the screen now is an example of a pair of redundant central controllers. And what you're seeing here is These controllers are monitoring each other, in this case, via physical heartbeat. This could also, however, be a network heartbeat as well. And then this is actually a case where when the controller dies, we've set this up via some relay logic where you could quite literally have all the IO transfer over to the other controller. I'd say that this scheme is certainly one that we used years ago, but is less common these days. A lot of this is happening instead of hardwire, rather over automation. So these two controllers might be managers that are talking to each other over a network, and they don't necessarily have critical IO on them. But what happens is if one fails, the other one takes over the control loops, and it sends the requirements of those loops down to lower level controllers where, physical changes are made via the IO. One of the challenges with DDC systems can be the synchronization of these controllers, but as I mentioned a few minutes ago, they're getting better in that realm, and there can also be schemes that you can implement as a programmer or designer to address that. For instance, a lot of these PID loops that are integral to these sort of controllers allow you to feed in a bias term, and that bias term in the PID loop allows it to be the case that such that if one were to fail and the other one were to start up, that bias can be used as a kind of the starting point of the loop, so you get a smooth transition from one to the other. If you don't have fully redundant controllers for a given function, you have what I was mentioning earlier, which is a distributed fail-safe scheme, which would mean, again, if in that example I provided with multiple air handlers, if one controller were to fail, well, you're losing automation to that air handler. But the benefit there is that the impact of that distributed scheme, the benefit of the distributed scheme is the impact of the failure is isolated to a single device. And the impacts in the case of an air handler can certainly be mitigated by thinking through what you want to happen when that failure occurs. So we can set up VFDs as an example to hold last known speed. So it just keeps humming along at whatever speed it was operating at before. We can configure our control valves to be in a fail last position. So an example of a chilled water air handler, the valve won't open or close and perhaps cause a capacity problem as a result. It'll just stick where it was, so that when that failure occurs, the dampers stay where they were, the valve stays where it was, and the fans stay where they were. And so that there's not a sudden step change in how we're controlling things when we lose that automation, giving operators plenty of time to respond to that failure. And again, because we have distributed control, all the other air handlers in the data hall continue to hum along and do what they're supposed to. It's also the case that we'll typically marry some level of distributed fail-safe control with central supervisory control where we might have redundancy. So using, again, that example of air handlers, we might have a set of redundant managers in that white space that are monitoring all of the air handler controllers, and they're being used to synchronize things like speed control across all the air handlers. And we'll see, we know that air handler is offline, and therefore we can take appropriate means at the central level to perhaps control the other air handlers differently if we wanted to. To minimize the risk associated with controller failures when using distributed fail-safe control, it can make sense to think about device lineups. So if we use a chilled water plant as an example, we might have 4 chillers, 4 cooling towers, 4 chilled water pumps, and 4 condenser water pumps. Well, we wouldn't want to put all the condenser water pumps on one controller and all the chilled water pumps on one controller. Instead, what we can do is put one of each device type on one controller, such that if we lost that controller, we're only losing a fourth of the automation for the plant, right? And we can continue controlling the remaining devices under automated control. So the next couple slides will just take you conceptually through how we might set up networks or control networks for a PLC approach versus a DDC approach for the same system where we have different constraints. So with a PLC scheme, this particular facility we're looking at has a central plant with chillers and cooling towers, and down at the data hall level, we are, say, using a flooded aisle design that has air handlers that are serving all of the racks. And so at the plant level, the scheme we would likely elect would be one where we have redundant central controllers that are providing all of the high level control functions for that plant. So staging chillers, determining what the appropriate pump speeds are, staging towers, determining the appropriate tower fan speeds, all of that stuff would be handled by those redundant central controllers. And then the commands would be sent out to the IO, which would be connected to remote IO panels or RIO panels via a ring network, such that if any communication wire were cut we still have communication to the path of those devices. And if either of the redundant controllers failed, we still have full automation via the other one. At the internal level, we would probably handle this in a similar way where we have redundant manager controllers. But maybe instead of these being just strictly IO panels down here, we have some level of automation at the air handler level. So each air handler might be independently, say, controlling its economizer dampers as an example. And in this case, if one of these controllers were to fail, we would likely have fail-safe responses for that air handler. But a lot of the actual control responses would be driven top down from these redundant managers. If we did this same data center using a DDC approach, we might be losing the ability to have RIO panels. Those might not be an option. Or let's say we have a data center where, these controllers don't support ring topology. That's not necessarily the case for all DDC controllers. As I mentioned earlier, many are now supporting that, but not all. So in this case, what you're seeing is home runs to each of the lineup controllers, to which I have a chiller, a set of pumps, and a tower, such that if any one of these controllers goes offline, I still have 3/4 of the automation for the plant. So this is a form of distributed fail-safe control where I'm limiting the purview of each controller to minimize the risk of an outage. And similarly, at the data hall level, we're doing the same thing. We have a controller specific to each air handler. And at both of these, we have one of these controllers acting as the manager, coordinating supervisory control functions. So it certainly is the case that if, say, the manager goes offline, you need to have programming at each of the individual controllers to have appropriate responses under the loss of that manager. Okay. Related to distributed fail-safe control is making sure that your devices do what you want them to in the event that you do lose automation. So say my controller dies. So the two scenarios you need to worry about are a controller dying. And so that you no longer have a device that's determining what the appropriate outputs are to your digital outputs and your analog outputs. And the other one would be control power failure. So maybe the controller itself could have stayed online, but instead what you actually lose is power to your controlled devices, your actuators, your valves, etc. And so you need to think through what happens in either of those scenarios. And with VFDs, you have a lot of flexibility, and they can be configured on a loss of command to retain last known speed, some fail-safe speed to turn off. And these things are something you should have in your specification so that the contractors know how to configure the devices in the field during commissioning. Chillers are similar in the sense that you can configure them to hold last known speed set point. You can configure them to either stay on enabled or to turn off. Likely you wouldn't want that. And with older machines, even if you can't maintain last known state over a network interface, like a backnet interface, you can still be clever with your relay logic to achieve the same thing. So here's an example of some latching relay logic that we've used on a job with network interfaces that didn't allow us to maintain last known command. So we'd use this such that if the controller died, the chiller would retain its hardwired enable command irrespective of what's going on with that controller's power. You need to think through these scenarios with dampers and valve actuators as well. There are two scenarios to think through. One is whether you're losing control power, and the other is whether you're losing the control signal. So what's the distinction? If I have say an analog actuator, there's actually the 24 volts that I'm giving that actuator so it has enough power to move its little servo motor. And then there's the control signal that I'm sending to that device to tell the actuator what to do. That signal is often a 4 to 20 milliamp signal, or a 2 to 10 volt signal, or a 0 to 10 volt signal. And we need to think through what happens if that control signal dies, so it goes to 0, perhaps, or what happens if we lose power to the actuator. And based on what you want your fail-safe configuration to be under both a control signal failure and a control power failure, you can determine whether you need your actuator to be spring return or fail last, and how you need to configure the action of that actuator, whether it should scale from open to close from 0 to 10 volts, or should be closed to open from 10 to 0 volts, etc. This table kind of summarizes that. In the interest of time, I'm not going to go through all of these options. When it comes to sensors, it's critically important, no different than your actual central equipment, that you specify redundancy where it's required to maintain automation. Sensors redundant sensors do add a little bit of complexity, but they add a lot of value in terms of fault tolerance for little cost. Critical sensors are those that are used for control variables that impact the way downstream systems work. So an example would be a chilled water differential pressure sensor. This is going to be absolutely critical to make sure that we have sufficient pressure and therefore flow to air handlers in a system. If we have a single differential pressure sensor, and let's say that sensor fails high, well, our pumps are going to go, oh, we're providing sufficient DP, and they're going to back off as a result, potentially starving the loads. So having redundant sensors there is obviously absolutely critical. When it comes to writing sequences of operation, it's important to reduce the number of sensors you're relying on. The fewer the sensors that you're relying on, the fewer places there are for your sequences to fail. And maybe it goes without saying, but to the extent possible, you should avoid relying on unreliable sensors. So things like humidity sensors that tend to go out of calibration or flow meters. And if you do need to rely on these sort of sensors, make sure you have the appropriate redundancy built in. You also need to think through built-in suspenders. What happens if a sensor fails? If the sensor fails and there's a redundant sensor, well, it might be fairly straightforward what you do. If, on the other hand, you have a sensor that fails, but it has some important function and there's no backup, well, your sequences need to specify what happens in the event of that failure. And another consideration for sequences is employing rolling redundancy whenever possible. Well, what does this mean? In the context of a chilled water plant, as an example, it may be that the current pressure and flow requirements only need you to run one chilled water pump. It may even be that one chilled water pump would be the most efficient way to serve the loads under that condition because you'd be at the right spot on the pump curve. But running only one pump in a data center context puts you at risk. Even if you have backup pumps, what happens if that pump fails? Well, there's going to be a time between the time the pump fails and the backup pump ramps up where you're going to potentially trip chillers and lose flow to downstream systems that could be problematic in the white space. The efficiency benefit isn't the main concern in this case. What we really care about is making sure that we have rolling redundancy. So we want to have at least two chilled water pumps operating at all times so that if one fails, we still have at least one online and it can speed up to catch the load while we're waiting for a backup pump to turn on. Alarms. Alarms are often an afterthought because if in theory, if sequences are working well, they're just telling operators what's going on so they can respond to it. But, we find that alarms shouldn't be an afterthought because there are certainly critical cases where operators do need to put things in hand and take over. And we found that alarms, no different from control loops, need to be appropriately tuned during the commissioning process. If there are poorly specified alarms or poorly tuned alarms, we find that operators get inundated with nuisance alarms that desensitize them. If you're operating a facility that has hundreds of alarms per day, but you know that most of them are meaningless, it's going to make it much more difficult for you to sort through the haystack and find the one needle that matters and actually respond appropriately. We think there are a few different techniques that you can employ in your designs to help mitigate or minimize the number of nuisance alarms operators have to deal with and to allow them to quickly identify what's important and what's not. One strategy is to establish multiple alarm levels, somewhere between 3 and 5 alarm levels. ASHRAE Guideline 36 and its sequences uses 4. These should be appropriately thought through and assigned to each alarm so that it's clear to operators what's a life safety issue, what's a critical issue that's going to prevent the data center from continuing to operate and maintain thermal control, what is a maintenance issue. These need to be clearly specified when assigning alarms to different buckets. Including features like appropriate entry delays is also important. Is it a big deal if your chilled water supply temperature goes above set point by 1 degree for 10 seconds? Probably not. But if you're constantly sitting above set point for 10 minutes, yes. Or if the chilled water supply temperature goes above set point by 5 degrees for 1 minute, well, that's probably enough. So thinking through those entry delays is critical. Having appropriate exit deadbands is also important. So this would be, okay, I come into alarm when I'm, say, 3 degrees above set point. I shouldn't go out of alarm until I'm less than 1 degree set point. Introducing suppression periods. So if we have some sort of alarm that is going to be latching, meaning it stays on the console until an operator acknowledges it. Well, we might also want to introduce a suppression period of, say, an hour, such that that alarm doesn't come in a zillion times. The operator just needs to see it once, and if it's critical, they know they need to address it. Instead of getting inundated with 40 alarms, it might make it difficult for them to find another needle that's important in that haystack. Another strategy is hierarchical alarm suppression. And so this would be, if there is an issue that we know is at the plant, alarm at the plant level, don't also alarm at all the downstream air handler levels, because the critical issue is originating at the plant. And finally is this concept of disparity alarms. So anytime we have redundant sensors, we can compare those sensors against each other in order to alarm on a calibration issue. Or if we have 3 sensors, we can triangulate on actually which one has failed and take it out of logic automatically and let operators know. So when it comes to commissioning, all of this controls complication. We find that the money tasks in the commissioning process are functional testing and trend review and simulator functional testing or bench testing. And so these are the ones where most of the critical issues with controls are identified. Simulator testing is particularly important on retrofit projects where you're going to be cutting over your controls live. You need to make sure that all of the kinks have been worked out before they actually get put into place in the field. When you're developing functional tests, you need to make sure that they simulate real world events as closely as possible. In data center context, a lot of times that means, if you can, leveraging things like load banks, which are basically giant electric resistance heaters that let you mock up IT loads to allow you to take the system through its paces. And all unique sequences of operations that could reasonably occur should be tested during functional testing of a data center. Trend review, on the other hand, is critical after functional testing to catch tuning issues and flawed sequences that couldn't have been identified during functional testing. So it's not possible to tell, for instance, whether a PID loop is well tuned across a range of load conditions during functional testing. But as a data center gets loaded up, that will be readily apparent during trend review. All right, with the remaining portion of the class here, we're going to transition into discussing retrofits and heat recovery. And I'll take you quickly through an example of a waterside economizer retrofit, and then Jeff will take you through many other examples. So this is going to probably be the last poll for me. And what we're demonstrating here is an example of a waterside economizer retrofit. There are 2 ways this retrofit could occur. So essentially what we're installing as part of a waterside economizer retrofit in this case is the plate and frame heat exchanger. And when this retrofit occurs, our question for you is whether it should be piped as we've shown it in option A, the heat exchanger in this location relative to the piping distribution, or as shown in option B as shown here. So I'll leave this up for just a second and then give you guys a chance to respond to the poll. Feel free also, actually in the interest of time, just to paste what you think the correct answer is into the chat, and I'll summarize what I'm getting from you guys that way. So I'm waiting on that. I see a question from one of the participants asking if there's a good resource for data center FPT scripts. I haven't found one. If it exists, we tend to write all of our FPT scripts in-house. I don't know if Jeff, if you have a different perspective on that.
Yeah, ditto.
I think there is some hope that we will have, at least for guideline 36 sequences, many of which can be applied to data centers, good functional test scripts at some point in the future, whether that ends up being work that somebody does for free or if it's work that ultimately gets funded through an ASHRAE research project, I think is to be determined at this point. All right. So right now I've got just 2 answers. One person thought it was option A, one person thought it was option B. And the correct answer in this case is option B. And the reason is that option B allows us to operate the waterside economizer in what we'll call an integrated fashion, which means that we can use it concurrently with the chillers to meet load. The option A on the left makes it a bit more difficult to do that. In fact, there are certain conditions where it just frankly won't be possible to operate in an integrated fashion. And I'll take you through that with some example numbers. So looking first at option A, which we'll call a non-integrated waterside economizer, essentially what we're doing is putting the heat exchanger in parallel with the chillers. Let's imagine we have an operating condition where we're sending 44 degrees out to the loads. Bear with me. I know that's colder than what would be typical for a data center, but for the purposes of this example, it's useful. And then 60 degrees coming back from the loads. Well, in this case, our chillers are making 44-degree water to serve those loads, but it's also the case that our waterside economizer would need to be doing the same to meet the loads. But let's say the ambient wet bulb temperature is 36 degrees Fahrenheit. Well, maybe that means we have a 5-degree approach, our towers can make 41-degree water. Then we're good, because our heat exchanger might have a designed 3-degree approach, and we can also make 44-degree water coming off that heat exchanger. So no problem in this example operating scenario. But what happens if the ambient wet bulb was a bit higher? Let's say it's 41 degrees. Well, again, we had that 5-degree approach across our towers. So now we're making 46-degree water with the towers. We have a 3-degree approach on the heat exchanger, which means that our plate and frame heat exchanger can only supply 49 degrees off the economizer. So now we're blending 49-degree water off the economizer with 44-degree water off the chillers. And so we're going to be supplying something greater than 46 degrees Fahrenheit out to loads. I mean, we could try to get clever with this and reset our chilled water supply temperature set point for the chillers such that we're still hitting 44 degrees going out to the loads. But we're there's a chiller efficiency hit as a result of that. And at a certain point, we're limited by freeze protection, right? Most chillers aren't going to allow us to operate our chillers below, say, 39 degrees Fahrenheit. So this scheme limits the utility of the waterside economizer heat exchanger greatly. If, on the other hand, we go with option B, what we're doing is creating an integrated operating configuration. So such that in this exact same scenario where our ambient wet bulb is 41, so we got 46 coming off the towers and we got 49 coming off our heat exchanger, that's not a problem, because what we've done is take 60-degree water coming back from the loads, first cool it down to 49 degrees with our plate and frame heat exchanger, and then send that 49-degree water to our chillers where it's cooled down to 44 before getting. So basically all of the water gets cooled down to 44 while we're maximizing the utility of the heat exchanger. As a general rule, you guys should be doing it this way. If this were a primary only system, what you'd see here instead of this, the second set of pumps would be making sure that the minimum flow bypass is located here and not on the other side down here of the heat exchanger. So that's a gotcha that I've made the mistake on in one job in the past. Clearing out those markups there. You can do this strategy in a retrofit context by either installing this control valve V1 or installing a side stream pump. In general, adding a valve is going to make controls a bit easier than adding a pump, but you may already be constrained by the amount of head that your secondary distribution pumps have, in which case you would use the side stream pump solution to avoid adding that extra pressure drop to the secondary loop. All right, so I'm going to skip through this because we're getting short on time, but there are a ton of details here regarding some of the do's and don'ts for implementing waterside economizers. So this might be useful for your future reference. We also have some ASHRAE journal papers, 3 of them, I think, on our website where we talk about implementing waterside economizers. So if this is a topic that's germane to you, please do dive into those articles, which are obviously all free.
Okay. Retrofitting waterside economizers. So this is a plant we worked on several years ago now that had a couple of 2,000-ton chillers, I believe, and provision to add a couple more. And while we were evaluating adding the chillers, we looked at, hey, what if we put in a waterside economizer? These chillers are running an E760 in Silicon Valley to serve data center type loads. And we were able to fit in a waterside economizer in the same plant that was able to meet the whole, I think it was about a 5,000-ton load. So this is like a 10,000 GPM waterside economizer, right, with 20-inch taps in just a tiny spare piece of real estate that we found in the plant. And that allowed us to reduce annual energy use dramatically. I think was something like 30% annually plant energy. So huge potential energy savings with a water economizer, and can be added to almost any existing plant. You just need to tie in to both the chill water and the condenser water side, but it's usually not that hard to find a good place to tie in. Here's me standing in front of our 10,000 GPM heat exchanger. So water economizers is a great retrofit opportunity for data centers, and it also fixing water economizers. We've gone into data centers and that have water economizers that never worked because they were piped non-integrated in a climate where it was very hard to get any 100% economizer hours. And with some fairly simple repiping, you can convert a non-integrated to an integrated economizer and get all the benefit of that. But what else can you do in an existing data center? Airflow management. We'll go through some strategies there. Things like containment, huge energy benefits there, and capacity benefits. VAV conversion of fan, legacy data centers, particularly if they're chill water, converting chill water cray unit from constant speed to variable speed is a really low-hanging fruit, if you will. We've done this now on literally hundreds of cray units and never had a single motor failure, even motors that were nominally inverter duty type motors. Full or partial air economizer retrofits. An air economizer doesn't need to be 100% sized. If you can't get 100% outside air, 50% or even 30% outside air is pure gravy, if you will, in an energy saving context. We've actually done direct evap cooling retrofits to air handlers, like chill water units, that adding direct evap cooling allowed us to basically eliminate the chill water energy use. Tap into the house air system. So if you've got a server room, computer room inside an office building, for example, you can use the house air system to provide a either full or partial air economizer, right? You might have crack units in your data center, but you might have the ability to use some house air to get some amount of air economizing. Sequence upgrades. Data centers aren't necessarily running the most efficient possible, especially some of the older legacy ones, and there's some easy low-hanging fruit there. And why retrofit is not just for energy efficiency. Hotspots is a big one, right? You might have issues where you're simply having IT failures or IT issues because it's hot in certain locations in the data center. And that's where things like retrofitting containment can be used. That can increase capacity. We talked about when you don't have containment, how you need to blow a lot more air. And so that's a way to get more capacity out of your data center. Cost effectiveness. There's a lot of utility programs out there for incentives to do retrofits. They're often based on measured savings, and often that's a fairly easy thing to do in a data center where you often have a fair amount of monitoring that you can leverage to get a utility rebate. Okay, airflow management. Even if you have containment, over time, there's sort of entropy in a lot of data centers, particularly ones that have a lot of churn, where you'll have holes in the rack basically where a server has been removed and nothing has been put back. Another one hasn't been installed. And so now you've got a hole in your containment. And there are simple blanking plates that you can put in to seal off unused U's in a rack. So that's a real simple one. Plug holes in the floor. Holes get added for cabling very often. And the more holes you have, the more leakage you're going to have. So that's an easy one. Remove unused cables. Raised floor data centers. Over time, there may be cables that are not being used that are under the floor. They can literally like clog up your underfloor, restrict your airflow, cause hot spots, require more fan energy to fight through the cabling. Add partitions for containment. Let's show some examples. Convert to high flow tiles and lower pressure. Again, legacy data centers are usually using the original Tate tiles that have a free area of like 25, 30%. And so you need a certain amount of pressure under the floor to get enough air out of those. There are high flow tiles that have free areas of upwards of 60, 70%. And so you get a lot more air out of it at a lower floor pressure. And when you lower the floor pressure, then you get less leakage through the holes, right? So sort of a double benefit there. More tiles and cold aisles. Even with high flow tiles, the more turf tiles you have, the less pressure you need under the floor. So again, lowering floor pressure reduces leakage, reduces fan energy. Add chimneys to cracks. I'll show you some examples of that. So this is a retrofit, but also a new construction. Actually, it's a requirement in Title 24 in a lot of cases. And it has to do with using house air, if you will, for small IT rooms like IDF closets. So what we always do, or almost always do, is wherever we have a small IT room in a building, we'll have some sort of dedicated system like a split system fan coil, DX fan coil, but then we'll also serve that same space with a VAV box and off of the house air system. And what this does is it provides not only a form of redundancy, but a form of energy efficiency. And we don't size the air handling system on the roof necessarily for the airflow of this VAV box, because if 99% of the time this is available as sort of a backup to the VAV box. And so we usually use the VAV as primary cooling when the air handler is able to do economizing. But if for some reason the air handler is fully loaded or there's a lot of load elsewhere in the building, it's usually because it's hot out. You're not going to get much economizing benefit out of this. So you shut off the VAV box, run your fan coil. Of course, you could size your air handler for it, but we find it necessarily cost effective. And as I said, this is actually required in Title 24 that anytime you have a server room over a pretty small amount, I think it's only like 3 kW or something. If you've got a house air system, you need to put a VAV box into that room. Same concept where instead of the VAV box going directly into the space, you can tie into the same ductwork that might be served by, say, a fan coil. You just would need to put a backdraft damper on your fan coil. So if it failed, VAV serve the space and not backdraft. Here's another simple retrofit. If you do have crack units or cray units that are constant flow, constant speed, and you're at low load and you shut some of those off, they backdraft. They don't have a damper on them. And so other units that are running, you're just going to be short circuiting through these ones that are off. So you need to cap them. And here was a very simple cloth cap that could be quickly dropped into place. Of course, a much better strategy is to put VFDs on the fans and run all of them at low speed. But with DX units, that's a little more tricky than it is with chill water units. So hot aisle containment, we've done a lot of projects going into existing data centers and retrofitting containment. And that can be done with hard partitions. It can also be done with vinyl curtain, like you would have in a clean room, or even in like a freezer, walk-in type freezer setup. And the preferred option is hot aisle typically. And so this is showing a raised floor system where we added partition, or you could add partitions above the racks, add some method to get into the ceiling as a return plenum, and then added what we call a chimney or a top hat to the cray or crack units to pull from the ceiling. So make the ceiling a return plenum. One of the features you can get with these types of curtains is a fusible link. So one of the big challenges with containment is fire protection. The sprinkler heads in your space, if it wasn't designed for containment, the sprinkler heads aren't going to necessarily be aligned with the containment. And so you might end up with a scenario where you've created a fire code violation by not having a sprinkler head within what's now effectively a room. And one way to get around that is to use fusible links that literally drop the curtain, let go of the curtain when it gets to a certain temperature, if there were a fire scenario. So that's an approved method of dealing with it. Of course, you can always add sprinkler heads and relocate them as necessary, but this is a way to do that in a live data center without having to get into your sprinkler head. This is another product out there for creating a lid for containment that you could use for like IRCs. It has the same, I believe, ability to peel back in the event of a fire. So you're going to deal with the fire sprinkler, relocating. Talked about those shields, those fusible links. Here's an example where we retrofitted curtains with fusible links. Here's another example, before and after. So this was a raised floor data center, chill water cray units around the perimeter that just used the space as a return through the space. And then we retrofitted the curtains, tied what were then hot aisles into the ceiling plenum, and added sheet metal top hats onto the cray units to use this ceiling as a return plenum. That allowed us to operate the cray unit at a higher supplier temperature to get more capacity, because now our airflow of the cray units can be more closely matched with the airflow of the racks. This is actually the same data center where we did a few different things. Besides adding that containment, we tied into the house air system. So this was the data center, which took up about a third or so of one of the floors in that office building. This was from the central system. The main supply main for that floor happened to go right through the data center. And so we literally just cut dampers into the main that dumped air into the cold aisle. We put control dampers on them. And nights and weekends, for example, when the air handler didn't have much other load to serve, when it's nice and cool out, you were getting lots of economizer free cooling. Obviously, the air handler wasn't necessarily sized for this load. And so in peak conditions, we simply shut those off, and the data center entire load was served by these cray units or AC units. Okay, so those are some of the retrofit opportunities that we found in data centers. Now we're going to talk about heat recovery. A data center is basically a whole bunch of toasters in a room. You've got lots of heat, and it needs lots of cooling, right, or fresh air to remove that heat. What if there was some other use for that? One of my favorite forms of heat recovery from a data center is if your office happens to be a dual duct system, or if you design it as a dual duct system where you have a a hot deck and a cold deck, you can take air right out of the hot aisles from your data center and literally transfer it directly to your hot deck of your air handlers. And so here's a schematic of a data center that has hot aisle containment, right? We've got perimeter spray units pulling out. This was actually ducted return. So not using the ceiling, but using ductwork. And then we basically just tied into that return ductwork and had it sent to the supply deck of the hot deck supply fan. The air got directly transferred to be used for heating. Of course, if you're pulling air out of the data center, you need to make it up, right? So that you don't have pressurization issues. And that's a very simple thing to do by simply using a VAV box off of the cold deck of your dual duct system. So not only does it give you an easy way to do makeup, but it also gives you some free cooling, because when you need that heating for your spaces, you're also going to be getting free cooling, right? It's cold outside, so your air handler is on economizer and you use free cooling. It's a small amount relative to the total cooling capacity, but again, it's free, right? Why not use it? Same concept. Here's a section view through a building that was an office that had a data center on the ground floor. Air handlers serving, this was an air handler dedicated to the data center. Then there were air handlers that were serving cold deck. And the hot deck was an air handler that was literally just in a mechanical room. And it pulled air either from the ceiling of the space and heated up with an electric resistance coil as a backup. The primary heating is just from the data center. The data center return ceiling plenum was connected to this deck air handler, and it just pulled air out of the data center ceiling, distributed it to the dual duct boxes, right, to heat the space. And the makeup for the air that got pulled out of here came from this air handler, which had an air economizer on it. In winter time, it just brought in a little bit more outside air, or is probably on 100% outside air already. And it just had to run less relief because some of that air was being relieved into this air handler hot deck. Another form of heat recovery we've used on small spaces. Here's an IDF room in a large lab building, actually, was to duct the ceiling to parallel fan powered boxes. And so these fan boxes, I believe, also had hot water coils. There was hot water reheat elsewhere in the building, right? Like here's a hot water reheat. But in the locations where we had IDF closets, IDF rooms in close proximity to other zones, we pulled the secondary air for the VA parallel fan boxes out of that space. And so most of the heating from this space, for example, is done by pulling the hot air out of this IDF room and directly transferring it to an adjacent space. Other forms of heat recovery chiller. So you can boost data center chill water return temperature from 80 degrees, for example, up to 110 or 140 or even 170 degrees, and then use that as hot water to your VAV reed boxes, for example, or to your fuel fan or to radiant heating or other types of heating sources. So even if you don't transfer the air directly, you can transfer heat from the chill water system, reduce load on your cooling towers, for example, by rejecting heat to your heating system. And there's a new requirement actually in Title 24, 2025, which goes into effect, I think, not until January 26th, that if you have a large building that has a good sized computer room or other types of process loads or process heating, like large domestic hot water for showers or kitchen, that you need to have a heat recovery chiller as part of your design. And this is basically sort of recognized, it was sort of built around the scenario of a good sized computer room in a good sized office building. And that it's a very efficient way to use that computer room to heat the building. There is an exception, by the way, in this requirement if you are doing the direct heat transfer. So you don't have to put in a heat recovery chiller if you're just transferring the air directly, like in a dual duct system. You can pipe hot water from your liquid cooling racks. If it's literally 110 to 140 degree water, you don't need the heat recovery chiller. Like you can send that water directly to a VAV read system, right? Without a heat pump. District heating. So there are locations in Europe, for example, where you can't actually even build a data center unless you connect it to a district heating system or some other source or sink for that waste heat. Personally, I haven't worked on one that tied into a district heating system, but the concept is pretty simple, similar to what we talked about here for the heat recovery chiller. You can basically pull heat out of your hot water system, your chill water system, or you can pull heat out of your exhaust air stream, right? If you're doing air like direct evap cooling, for example, you're still exhausting a good amount of air that can be over 100 degrees. You can put coils in that stream and then either provide that water directly or boost it with a heat pump chiller and use it for district heating. A couple other tricks we've seen is that generators use quite a bit amount of electric power to keep the crankcase heaters at temperature, especially if a generator is outdoors. There's a pretty significant consumption of electricity by the electric resistance heaters in that crankcase heater. And a clever solution or way to reduce that amount of heat load is to run your exhaust air. If you've got air side economizing, if the generators can be located indoors, run the exhaust air through the generator room. Keep your generator room at 90 to 100 degrees, and that will keep your crankcase heaters from having to consume electricity to keep your generator ready at a moment's notice. Divert chilled water return through the generator water jacket heater. This is another scheme. Instead of using air, to use hot return water to keep the generator at temperature. And then water source heat pumps or VRF systems. So you can put, for example, a VRF unit in your data center and use that as a way to recover heat to heat other spaces. You can also similarly put a water source heat pump to cool the data center that then transfers heat to heat pumps heating other spaces in the building. Here's a schematic illustrating the heat recovery chiller concept, and it's a pretty basic concept. So if you had a simple system using water-cooled chillers to cool your building, to pull heat out of the building, and gas boilers to put heat into your building, you can tie these two together. And instead of cooling the building with the chillers, you can add a heat recovery chiller. It doesn't need to be tied to the cooling towers because its heat rejection is to the hot water system. So here's a plan view of a office building where we looked at retrofitting a heat recovery chiller. Here's the chillers right next to the boilers. And here's those pipes from the previous scheme that allowed us to tie into the hot water return upstream of the boilers and the chill water return upstream of the chillers. And again, this wasn't designed for it, but we found a nice space within our boiler room to fit in our heat recovery chiller and reduce. Basically, it was going to eliminate the entire annual energy use of the boilers and do all the heating for the building by transferring waste heat from the data center to the hot water system. This is our last slide, and it is a schematic of a further evolution of that heat recovery chiller concept that we call a tier system, time independent energy recovery. And the big advantage of this is that it can do heat recovery, but it can also store heat for use at a different time. The previous schemes all required simultaneous heating and cooling loads. What we've found is, of course, that in lots of buildings, you might have a heating load in the morning, but not a simultaneous cooling load. The cooling might not happen until the afternoon. And so this is a scheme that we've actually implemented in a few buildings now that allows us to store heat from our chillers in a condenser water storage tank and then pull heat out of it with heat recovery chillers and send it into the building, say the next morning when we're in morning warm up. And these chillers have the ability to do simultaneous heating and cooling, but also non-simultaneous, where we're storing heat in a tank and then pulling it out later. And we use these as a decarbonization strategy in new buildings as a way to reduce the number of air source heat pumps that you would need on the building. So what we found actually is that thermal storage ends up being less expensive than using just heat pumps for heating, because it allows us to get away with a lot fewer of these heat pumps. We're able to store heat both from heat pumps on the worst case heating condition, but also from cooling from the day before, for example. And so it's kind of a double win. It's a lower cost system, and it's a lot more efficient because it allows simultaneous and non-simultaneous heat recovery. So we're right at time. Brandon and I are happy to hang out for a few minutes and answer questions. I believe everyone is also able to unmute themselves. Question here from an architecture student: like to get into data center design. Passive house design certification would be helpful in that regard. I'm not sure I know the connection between passive house design and a data center. Most of the data centers we work with, if it's a dedicated data center building, has no windows, for example, right? And so the envelope is not really part of the equation. You're generally dealing just with internal loads, but maybe I'm missing there. Where are the big data centers being built for X? I don't have good statistics on where all the data centers are going. I can just tell you from our experience that it's common to put data centers in places where power is cheaper, where construction costs are cheaper. So we see a lot of data centers in places like Utah and Nevada, but we've seen them all over the country. The data center capital of the world happens to be a place called Ashburn, Virginia. And that's because it happens to be at some sort of special node on the internet, which beyond my pay grade, but there's a ton of data centers in that location. It's right now it's exploding, especially with AI, and we're seeing them all over the country, but generally in somewhat more remote, less expensive location.
Oh, well, thanks for sticking with us through 6.5 hours of instruction. Appreciate it. Of course, no problem.
Yeah. And our contact information is on the first slide. You should have access to the slide. So if you do have other questions, feel free to reach out to us.
Appreciate it. Thank you, guys.
All right.
All right. Thank you all.